Professor Von Schmohawk, and welcome to YU. In the previous lecture, we saw that when Gauss-Jordan elimination is used to transform a matrix that represents a dependent system of linear equations, the result will be an independent system of fewer equations from which the solution set can be easily determined. Although the planes corresponding to this new system may be different than the original planes, the solution set of the system will always be the same. In this lecture, we will look at one example from the previous lecture and see how the planes were transformed step by step from a system of three planes representing three equations, each containing three variables, to a system of two planes representing two equations, each containing only two variables. In this example, no two equations were multiples of each other. However, each one is in fact a linear combination of the other two, and so all three equations are dependent, although it would be very difficult to tell this just by looking at the equations. Now let's represent this system of equations as a matrix, and see what happens when we transform the matrix to reduced row echelon form. We start the process of Gauss-Jordan elimination by changing the first row's leading entry to a 1, using a scale operation to multiply row 1 by 1/4. As we saw in the lecture entitled A Geometrical View of Gauss-Jordan Elimination, scale operations have no effect on the planes. We then change the entry below to a 0, using a pivot to add -4 times row 1 to row 2. Since the pivot operation adds a multiple of row 1 to row 2, it causes plane 2 to rotate around its line of intersection with plane 1. And since the x-coefficient in row 2 has changed to 0, plane 2 has become parallel to the x-axis. We then change the entry below that to a 0, using a pivot to add -16 times row 1 to row 3. Since this pivot operation adds a multiple of row 1 to row 3, it causes plane 3 to rotate around its line of intersection with plane 1. And since the x-coefficient in row 3 has changed to 0, like plane 2, plane 3 has also become parallel to the x-axis. Since both planes 2 and 3 rotated around the same line of intersection to become parallel to the x-axis, both planes are now identical. You may notice that matrix rows 2 and 3 are now multiples of each other. Row 2 is 4/5 times row 3, and row 3 is 5/4 times row 2. We now move to the second column, changing, although it would be very difficult. As we saw in the lecture entitled A Geometrical View of Gauss-Jordan Elimination, scale operations have no effect on the planes. We then change the entry below to a 0, using a pivot. The pivot operation adds a multiple of row 1 to row 2. It causes plane 2 to rotate around its line of intersection with plane 1. And since the x-coefficient in row 2 has changed to 0, plane 2 has become its line of intersection to multiply row 2 by 1/16. Second column. You may notice that in row 3 has changed to 0, Like plane 2, plane 3 has also become parallel to the x-axis. Since both planes 2 and 3 rotated around the same line of intersection to become parallel to the x-axis, both planes are now identical. You may notice that matrix rows 2 and 3 are now multiples of each other. Row 2 is 4/5 times row 3, and row 3 is 5/4 times row 2. We now move to the second column, changing the second row's leading entry to a 1, using a scale operation to multiply row 2 by 1/16. We then change the entry below that to a 0, using a pivot to add -20 times row 2 to row 3. But since rows 2 and 3 were multiples of each other, the multiplier we picked for row 2 zeroed every entry in row 3. As a result, row 3 no longer describes a plane, and now we have a system consisting of only 2 planes. For this matrix to be in reduced row echelon form, each leading entry must be the only non-zero entry in its column. Although the leading entry for row 1 is the only non-zero entry in its column, the leading entry of row 2 is not. Therefore, we must change the entry above row 2's leading entry to a 0. We do this with another pivot, adding 1 times row 2 to row 1. Since this pivot added a multiple of row 2 to row 1, it causes plane 1 to rotate around its line of intersection with plane 2. And since the y coefficient in row 1 has changed to 0, plane 1 is now parallel to the y-axis. Since both leading entries in the matrix are now the only non-zero entry in their columns, this matrix is in reduced row echelon form. Converting this matrix back into equations, eliminating the terms with 0 coefficients, eliminating the coefficients of 1, and the equation 0 equals 0, we now have an equivalent system of 2 independent equations. So Gauss-Jordan elimination has created an equivalent independent system of 2 linear equations. The solutions of the system correspond to the infinite number of points contained in the intersection line of the 2 planes which correspond to these equations. And once again, this infinite solution set can be written in parametric form. So, although this system initially contained 3 distinct planes, because all 3 planes shared a common line of intersection, when Gauss-Jordan elimination caused planes 2 and 3 to rotate around this line to become parallel to the x-axis, planes 2 and 3 became identical. As the process continued, since rows 2 and 3 both described identical planes and were therefore multiples of each other, row 3 became 0, eliminating one dependent equation that described one of the identical planes. This resulted in an equivalent independent system composed of 2 intersecting planes. Finally, Gauss-Jordan elimination caused plane 1 to rotate around the intersection line to become parallel to the y-axis. The infinite solution set of this system, represented graphically by the intersection line, can now be written in parametric form, as we will see in the next lecture. Mohawk, and welcome to YU. In the lecture entitled Describing Infinite Solution Sets Parametrically, we saw how infinite solution sets could be described using parametric equations. In this lecture, we will show that once an augmented matrix representing a system of equations with infinitely many solutions has been transformed to reduced row echelon form, it is especially easy to produce a parametric description of those solutions. But before we describe the solutions of a system, we first need to know what type of solutions the system has. Is it possible to tell if a system has a single unique solution, no solutions, or infinitely many solutions, by simply looking at the matrix? The answer is yes, once the matrix is in reduced row echelon form. So let's see exactly how this is done. Given a reduced row echelon, So let's see exactly how this is done. Given a reduced row echelon matrix, the first step is to determine if the system is inconsistent, having no solutions. This is easy, since if the matrix contains any row which has all zero coefficient entries and a non-zero constant entry, then the system has no solutions. This can often be determined during Gauss-Jordan elimination, even before the process is finished and the matrix is in reduced row echelon form. Once we have eliminated the possibility that a system is inconsistent, we know that the system is consistent with one or more solutions. The next step is to determine whether the system has a single unique solution or infinitely many solutions. We can determine this by looking at the positions of what are called pivot columns. So what exactly is a pivot column? We know that in reduced row echelon matrices, the leftmost non-zero entry in each row, called the row's leading entry, must be a 1. The positions that these leading entries occupy in a matrix are called pivot positions, and the columns that contain these pivot positions are called pivot columns. The positions of these pivot columns tells us what type of solutions the system has. If every column to the left of the vertical line is a pivot column, then the system has a single unique solution. And if any column left of the vertical line is not a pivot column, then the system has infinitely many solutions. We have already seen that when a system has a single unique solution, it is easy to describe that solution simply by looking at the reduced row echelon form matrix. So how do we describe the solution set when there are infinitely many solutions? In the lecture describing infinite solution sets parametrically, we saw how to use parametric equations to describe an infinite solution set when using the elimination method. However, creating a parametric description from a reduced row echelon matrix is an even simpler process. In a reduced row echelon form matrix, the columns to the left of the vertical line each contains the coefficients for one variable. But among these columns, the pivot columns and their associated variables have a special significance. When creating a set of parametric equations, the variables associated with the pivot columns are treated as dependent variables, and the variables associated with the remaining columns are considered to be independent. In the parametric equations, the values of the dependent variables are expressed as functions of the independent variables, which can vary freely. For this reason, the independent variables are sometimes referred to as free variables. To create a parametric description of the system's solution set, we first convert the non-zero rows of the matrix into equations, the equations so that the dependent variables are alone on the left side. This gives us equations which express the dependent variables as functions of the free variables. But to express the solution set in parametric form, each variable in the system must be written as a function of parameters, which are a new set of independent variables created specifically to define the solution set. The first step is to equate each free variable to a parameter. So one parameter must be created for each free variable. For example, in this system, we can equate the free variable z to a parameter which we will call t. The second step is to replace all the free variables in the remaining equations by those parameters. So in this example, which express each system variable as a function of a single parameter, t. Creating this set of parametric equations was simple. Since each dependent variable had a coefficient of 1 and appeared in only one equation, it was a simple matter to rewrite those equations so that each equation equated one dependent variable to an expression containing only the free variable. That free variable was then set equal to an independent parameter, which could then replace the free variable in the other equations. expressing each system variable as a function of a single parameter t. In this example, there was only one column left of the vertical line that was not a pivot column, and so there was only one free variable. Our solutions therefore contained only one parameter. But now let's look at an example with more than one free variable, and thus more than one parameter. In the lecture, Gauss-Jordan elimination with dependent systems, we solved a system of three linear equations which were all multiples of each other. Once we expressed this system as a matrix and transformed it to reduced row echelon form, we found that the matrix represented an equivalent system consisting of a single equation in three variables. So how can we write a set of parametric equations for this solution set? Looking at the reduced row echelon matrix, we see that there is only one pivot position, and thus one pivot column. Since this pivot column corresponds to the variable x, x is the dependent variable, and y and z are free variables. Rewriting this equation so that the dependent variable x is alone on the left side, we then only need to equate the free variables y and z to parameters of our choosing. Let's call these two parameters s and t. We can then write the first equation in terms of s and t instead of y and z. The solution set of this system is now described by a group of parametric equations, which express each of the three variables as functions of the two parameters s and t. Now let's look at an example of a reduced row echelon matrix with 3 rows, but 5 columns to the left of the vertical line. This matrix therefore represents a system of 3 linear equations in 5 variables. It has 3 pivot positions, and the variable rearranging the equations so that the dependent variables are alone on the left side, dependent variables x, z, and v as functions of the free variables y and u. Again, call the other variables as functions of s and t instead of y and u. The solution set of this system is now described by parametric equations, which express the values of each of the 5 variables as functions of 2 parameters s and t. In the first example, the system of equations contained 3 variables x, y, and z, and so the system was graphically represented in 3 dimensions. However, the solution set of the system corresponded to a one-dimensional line. Since the solution was one-dimensional, its parametric representation required only a single parameter, t. As this parameter t varies from negative infinity to positive infinity, each unique value of t produces a unique set of values for x, y, and z. Each set of values is one solution of the system corresponding to one point on the line. In this example, the space containing the system and its solution set is 3-dimensional, because the system consists of equations in 3 variables x, y, and z. All the possible combinations of values of those variables correspond to all the possible points in this 3-dimensional space. However, the solution set of that system is a subset of those values, whose coordinates correspond to points on a one-dimensional line. This line can be thought of as a one-dimensional space embedded within the system's 3-dimensional all the possible points in this three-dimensional space. However, the solution set of that system is a subset of those values, whose coordinates correspond to points on a one-dimensional line. This line can be thought of as a one-dimensional space embedded within the system's three-dimensional space. A lower dimensional space like this, embedded within a space of higher dimension, is called a subspace. So the solution set of the system forms a subspace of lower dimension than the system itself, and the parameter t can be thought of as a single coordinate which locates a point within this subspace. The set of parametric equations are therefore a way to translate the values of that coordinate t into the values of the three coordinates x, y, and z, which locate the same point in the three-dimensional space, as the system consists of equations in three variables x, y, and z. All the possible combinations of values of those variables correspond to all the possible points in this three-dimensional space. However, the solution set of that system is a subset of those values, whose coordinates correspond to points on a one-dimensional line. This line can be thought of as a one-dimensional space embedded within the system's three-dimensional space. A lower dimensional space like this, embedded within a space of higher dimension, is called a subspace. So the solution set of the system forms a subspace of lower dimension than the system itself, and the parameter t can be thought of as a single coordinate which locates a point within this subspace. The set of parametric equations are therefore a way to translate the values of that coordinate t into the values of the three coordinates x, y, and z, which locate the same point in the three-dimensional space of the system of equations. The system of equations in the second example also contained three variables, and so the graph of this system also required three dimensions. However, the solution set of this system formed a two-dimensional plane. The parametric representation of the solution set therefore required two parameters, which we called s and t. As s and t each independently vary from negative infinity to positive infinity, each unique combination of values produces a unique set of values for x, y, and z. Each set of values is one solution of the system corresponding to one point on the plane. Although the space containing this system is three-dimensional, since the system consists of equations in three variables x, y, and z, the solution set of that system is a two-dimensional subspace embedded within that three-dimensional space. The parameters s and t can therefore be thought of as coordinates which locate a point within this two-dimensional subspace, and the parametric equations can be thought of as a way to translate the values of the two parameters s and t into the values of the three coordinates x, y, and z, which locate the same point in the three-dimensional space of the system of equations. In the third example, the system of equations contained five variables, and so graphing this system would require 5 dimensions. Not a very practical task in this universe. However, because the system had 2 free variables, the parametric representation of the solution set still required only 2 parameters, which we once again called s and t. The solution set of that system can therefore be thought of as a 2-dimensional subspace embedded within a 5-dimensional space and the parameters s and t can be thought of as coordinates which locate a point within the two-dimensional subspace. So even though it is impractical to visualize this system graphically, the parametric equations are a way to translate the values of the two parameters s and t into values of 5 coordinates x, y, z, u, and v, which locate the same point in the 5-dimensional space of the system of equations. So we have seen that in a reduced row echelon form matrix, the pivot columns divide the system variables into dependent variables and free variables. The number of free variables corresponds to the number of dimensions required to graphically represent the solution set. If there are 2 free variables, the infinite solution set will be graphically represented by a 2-dimensional plane. If there is 1 free variable, the infinite solution set will be represented by a 1-dimensional line. And if all columns left of the vertical line are pivot columns, there are no free variables, and the solution set will be a 0-dimensional point corresponding to a single unique solution. In the next lecture, we will use Gauss-Jordan elimination to transform systems of equations with no solutions and follow how its graphical representation changes during each step of the process.